Okay, the recording is now on. And as I was saying right before I turned on the recording, it's important to record today's session because what we're going to do today is the last piece of information that I can think of that you need to know before we take next week's test. It's some calculations that you'll be required to do for some of the test questions, and it's something that we have not talked about before. It's something that civil engineers need to know, but also it's not just civil engineers. If you go into mechanical engineering or chemical engineering, what we're going to talk about today is something that you will need to know. Now, if you go into electrical engineering or one of the other types of engineering, then you may or may not need to know it so much. But the idea of this class is that you probably don't know yet which engineering field you want to go into. And so we should all learn it. Okay, so let me share my screen with you. Oops, wrong click. Let me try this again. Okay. Okay, so as I said right before I turned on the recording, being able to analyze the forces that are acting on a structure like this is really important. You will need to know, you'll have to be able to calculate, is member A under tension or compression and how many pounds is it? Same thing with member C or D or B. You need to know, are they under tension or are they under compression, and how many pounds of tension or compression force are they feeling? But I think that you guys are pretty good at that. So I'm going to go ahead and leave that and go on to this next thing. All right, so what you're seeing right now is a picture kind of like what you'll probably see on the test next week. And this is something that here in Utah, you don't really see water towers like this very much. Although in the west side of the valley, I know there are a couple towers on the west side. But over on the east side, I'm not aware of any towers like this. This is a water tower. And a water tower is necessary to give you water pressure, so that when you open up the faucet in your kitchen sink or your bathtub or your garden hose or whatever, the water, in order for the water to come out, the water needs to be under pressure. If you live in Salt Lake City, especially if you live on the east side of the city, well, they don't have water towers like this, but they do have something that's the same thing. And what happens is up on the hillside, in the mountains on the east side of the city, they have great big water tanks up there. And so then the pipes run from those water tanks down to your home. And because of the water being in the tank there, that creates pressure so that when you turn on your faucet, water comes out. Now, if you live on the west side of the city, or if you live in Kansas or someplace like that where they don't have hills, then they have to build these artificial towers, and then they pump water into the tower. And so then gravity causes pressure so that when you turn on your faucet, then water comes out. Okay, so civil engineers are the ones who design the towers. But what we're going to focus on today is not so much the design of the tower. We're going to trust that somebody has built a tower. What we're going to focus on is calculating how much pressure the water is going to be in each of these homes. And the idea here is that home B is up on some little hill, whereas home A is down, in the lower part of the valley. So because home B is up higher, the water pressure in home B is going to be less than the water pressure is in home A. And so when you take the test, they're going to ask you to calculate, and they're going to ask you to come up with a number for what will the pressure be given the different numbers that you see on the screen here. Okay, so let me turn on annotation. Okay, so if the tank is completely full, so the water level is up here at the very highest level, so then the water level here, if you add these two numbers, you'll find out you get 90 feet. So this water level is 90 feet higher than the faucet in house A. And so we're going to use that together with some other things that we're going to learn in just a few minutes. And you can actually come up with a number for what the pressure is then in house A. Now house B is up higher. So you can see here, we've got 90 meters or 90 feet from here to here, but house B is up 24. So whatever 90 minus 24 is, so 66 feet, that's the number for house B. And so when we do the calculations that we're going to do in just a few minutes, 66 is the number that we're going to put into the calculations to find out what the pressure is for house B, whereas 90 is the number that we're going to put into the calculations to find out what the pressure is for house A. And then also we're going to learn about how to calculate how much water comes out depending on how big the hole is in your faucet. So these are things that when you learn that, well, when you look at the equation that you need to know, it looks pretty scary. This is the equation. It's called Bernoulli's equation. When you first see it, it looks pretty frightening. But let me tell you not to worry, because first off, you don't need to memorize this equation. When they give it to you on the test, they will tell you this is the equation to use. Okay. And so what you need to do is you just need to know how to use the equation. So you'll see there's a bunch of symbols here in the equation, like, there's a P. So you need to know what is that. And then there's this other thing that looks like it's a lowercase p. It's actually the Greek letter rho. Okay, this is the more correct way to write it, but the font that I've used in this particular PowerPoint slide, it makes it look like it's a lowercase p, but it's actually the Greek letter rho. So this lowercase p and this uppercase p are not the same. So you need to know what they are, and I'll tell you in just a minute. But you see, we've also got a V here, but it's a V1, and over here we got a V2, and here's that same lowercase p again, which is not really a lowercase p. It's actually the Greek letter rho. So let me write it. R-H-O is the way that it's pronounced. So from now on, this lowercase p here, I'm not going to call it a lowercase case p because it's not. I'm going to call it the Greek letter rho. Okay, so you guys, you need to know what rho is and how to use it. You need to know what the V's are, what the H's are. Okay, that's really important. So let's go ahead and let's learn what they are. Okay. All right. So here is a very simple example. It's just a punch dispenser. So what we got here is we got some water, some flavored water, but it's just water. This is the water level right here. So it's like, you think of it like this is the tower, okay? And this right here is the place where the water is going to come out. So when we pull on this handle, then the water comes flowing out, okay? So there's a couple things they might ask you. They might ask you, what is the pressure at the handle? Or they might ask you to calculate how fast the water is coming out when you open up the handle. Now, in the example that I've got right here, I'm assuming that what they're asking you is how fast will the water be coming out when you open up the handle. All right, so let's look at this equation. Let's look at Bernoulli's equation, and let's figure out what are the things that go in to Bernoulli's equation. All right, so the first thing is, hang on a sec, my annotation got a little weird on me there. Okay, so the first thing is the uppercase P. All right, that stands for pressure. Oh, wait a minute, am I recording this? Yeah, I'm still recording this, right? Okay, good. All right. Yeah, for a minute I was worried that I forgot to turn on the recording. Okay, the uppercase P here stands for the pressure. Now, at the top level here, this is open to the atmosphere. And now some of you, if you've taken chemistry, you should hopefully know that the air pressure that we're experiencing right now is not zero. It might feel like zero, but that's just because your body is used to it. Um, there is actually air pressing down on us at all the time. Um, but when an engineer measures pressure in a water, the normal practice is that we measure the pressure relative to atmospheric pressure. So if something is open to the pressure, or I'm sorry, if something is open to the atmosphere, then we would say that that is going to correspond to zero pressure. Not that it's zero absolute pressure. That's not the case. It's that it's zero relative pressure. And so when I ask you what is the pressure down in the water here, what I'm asking is how much pressure is that above atmospheric pressure? And in fact, you might, on the test, you might see things like PSI, which stands for pounds per square inch, and you might see PSIG, which means pounds per square inch gauge, where G stands for GUAGE, gauge pressure. And then you might see PSIA, where A stands for absolute pressure. Okay, so absolute pressure means that we cannot say that atmospheric pressure is zero. We have to recognize that atmospheric pressure is some non-zero number, and so whatever the pressure is in the water down here is the pressure that you get from the difference here plus whatever the atmospheric pressure is. So that's PSIA. Now, I don't think that they're going to give you any problems like that. I think all of the problems on the test, they're going to ask about gauge pressure. And so that means what is the pressure relative to atmospheric pressure? So in that case, you can safely assume that the pressure up at the top here is going to be zero. And the pressure that we're interested in down here is the pressure relative to atmospheric. Okay, so everything that you see on the left side of the equation applies for some point that I'm going to call position number 1. And so if we say that the top of the water is what we're going to define as our position number 1, then this P1 stands for what is the pressure at position number 1. And since our container is open up to the atmosphere, the pressure is 0. So that goes away. Now number 2 here. So let's say that this point right here is number 2. That pressure is not going to be 0 as long as the valve here is closed. So let's assume this valve here is closed. Okay. So there is going to be pressure there, so the pressure will not be 0. Okay. What is this thing that looks like a lowercase p, but it's actually the Greek letter rho? What is that? Well, some of you guys have taken chemistry, and so I know that you've talked about this in your chemistry class. Anybody want to unmute yourself and tell me? What does Coach Miller tell you rho stands for in chemistry? Come on, guys. Somebody needs to speak up here.
I don't think he's taught us that.
Yeah, I'm pretty sure he hasn't.
Oh, okay. Well, maybe he just hasn't gotten to it yet.
I was in his class like this morning, and I don't remember anything.
Okay. Well, anyway, rho is defined as, so when I put an equal sign with an extra line up above it, that means is defined as the density, or actually tell you what, let me just change that ever so slightly. What I'm going to say is, instead of saying is defined as, what I'm going to say rho is equal to the density, and density is defined as the mass divided by the volume. Okay, so let's suppose that I take a 1 gallon milk container, right? It's pretty heavy. It has a lot of mass. So the volume of that would be 1 gallon. And then the mass would be however many kilograms of mass that works out to be. Okay, let's suppose that I pour out the gasoline, let's suppose I pour out the milk and pour in a different liquid, like for instance, gasoline. Gasoline is less dense than milk. So a gallon of gasoline has less mass in it. It's gonna weigh less, okay? And if I pour out the gasoline and put in a bunch of feathers, so a gallon of feathers has very little density at all. Feathers don't weigh very much at all, okay? So rho stands for the density. And so in order for us to use this calculation, we're gonna need to know how much mass 1 gallon of this whatever liquid it is. Now, volume might not be measured in gallons. It might be measured in cubic feet or cubic meters or whatever, okay? So don't worry about memorizing what the density of various fluids is, because on the test, they will give it to you. And in the homework that I'm going to have you do tonight, I will just tell you, this is what rho is for this particular liquid. So you just need to know not to be scared when you see this equation. So rho is just a number that you will be given. Okay. Now, what about, so let me clean up my drawing here a little bit. Okay. What about V? So V1. What is V1? Well, if you've taken physics, which some of you have, you know that V is the letter that we normally use for the velocity of the liquid. So if nothing is moving, the water molecules up here at the top, well, the velocity is going to be 0. Okay, if the liquid is moving, if it's flowing at any speed, then the problem will tell you what that is. Okay. All right, so now we know what P is, we know what rho is, we know what V is. Here's that same rho again, and the rho here and the rho here are in fact the same. What is G? So Zaid, I know you've taken physics. Can you unmute yourself and tell us what is G?
G is gravity.
What about gravity? Is it the force
Oh.
of gravity or is it the acceleration due to gravity?
Gravity's acceleration, which is
Okay.
9.8.
Okay, all right, so G, so guys, if somebody asks you what is G, don't just say G is gravity. You have to say whether it's the force of gravity or whether it's the acceleration to gravity. And the answer is it's the acceleration. Okay, so Zaid remembers that 9.8 is the number that we used in physics, but be warned, that number only applies if you're measuring in meters per second per second. Okay, if you're using American units, which is what most engineers use. So American engineers don't usually measure distances in meters. They usually measure distances in feet. So if you're using American units, do not use 9.8. You need to use 32 because the acceleration due to gravity in feet per second is 32. So feet per second per second. So the reason I say feet per second is this. If I take my calculator and I hold it up here, the velocity is 0. If I let go of it and it starts accelerating downward, every second that goes by, then the calculator is going to be going at 9.8 meters per second faster than it was the previous second. Or if I'm measuring it in feet, it'll be going 32 feet per second faster than it was the previous second. So t equals 0. In fact, tell you what, let's share a whiteboard here. Okay. So if I were to make a graph of the velocity of the calculator or the rock or whatever it is as a function of time, okay, and I'm gonna have my velocity. I'm gonna do it in feet per second, or you might want to do it in meters per second. Okay, so at time t equals 0, that's when I'm just barely letting go of it. So right before I let it go, it's moving at 0 feet per second, which is also 0 meters per second. 1 second later, if I measured in feet per second, it's going to be going 32 feet per second. If I measured in meters per second, it's going to be going 9.8 meters per second. 1 second after that, it's going to be going another 32 meters per second. So it's going to be going 64. And this one here is going to be going at 19.9. A second after that, it's going to be moving at 96 meters per second. And then whatever 3 times 9.8 is. Okay, so you see every second that goes by, it increases by 9.8 meters per second. So that's why we say 9.8 meters per second, which is written as Peter per second squared. Or we say 32 feet per second, which is also written as feet per second squared. Okay. So let's go back into here again. Okay, so now we know what G is. G is just the acceleration due to gravity, right? So what is H? Well, H is the height of whatever that point is relative to whatever other ground level you want. Now, if this is point number 1 up here, and if down here is point number 2, we could measure everything relative to the tabletop, but an easier way to do it is take whatever is your lowest point and call that your H equals 0 point. Don't worry about the tabletop. Worry about whatever is the lowest point that you are worried about. So in that case, H2 is going to be 0, which means this whole term is going to go away. And H1 is just going to be whatever is the distance from your reference level up to however high point number 1 is. Okay. All right. So now that we know that, let's go in and let's say I'm not interested in the pressure. I'm interested in the velocity. I want to know that if I were to open up this valve right here and water comes spurting out, I want to know how fast will that water be moving. Now, when you look at this big ugly equation here, you might be scared that this is going to be a difficult problem. It's actually very easy. 9th grade level algebra is all you need to know in order to do this. Okay, so here's what we're going to do. We're going to go in and see where things are equal to 0 and see what we can cancel out of this equation. Okay, so if our container here is open to the atmosphere, that means that the pressure at point number 1 here is just going to be 0 because it's open to the atmosphere. Okay. If this water up here is not really moving, okay, I mean, when we open up the faucet and water starts coming out here, technically the water molecules up here will be moving slowly downward. But if this is a big container and this is a small opening, the velocity up here is going to be a number that's so close to 0 that we can call it 0. So this whole term just goes away. It's equal to 0 too. Now this guy right here, he's not 0. We'll come back and we'll get him in just a minute. Okay. Now, what about down here where the faucet is? Okay. If the faucet is closed, then the water right at the faucet is going to be feeling some pressure. But if this is open, if I open up the faucet so that it's open to the atmosphere, well, guess what? Anything that's open to the atmosphere, by definition, the pressure is 0. Now, remember, we're talking about the relative pressure, we're not talking about absolute pressure. It's all about relative pressure. Okay, so if water is coming out here, well, this velocity here is not going to be 0. So this term stays here. What about this term? Well, if we define that H equals 0 at this lower level here, then there's a 0 here, and anything times 0 is 0. So this equation that used to look so big and scary, it's not so big and scary after all. what we're left with is rho times G times H1 equals 1/2 times rho times V2 squared. And so you guys can see that this is just ninth grade algebra. Going from here to here is very easy to do. I mean, how did we do it? I mean, if you really want to see the steps, okay, I'm willing to show you the steps, okay? So what we've got is we got here, let me do it over here. We got rho GH equals 1/2 times rho times V2 squared. Okay, so I want to solve for V2. So what do? Well, if I multiply both sides by 2, then 2 cancels the 1/2. And then I need to divide both sides by rho. Okay, so that row up there and that row there cancel out. So they're gone. And so now I've got V2 squared. So what do I do to get rid of that? I take the square root. And what am I left with? Bingo. Velocity equals the square root of 2 times G times H. So this big ugly equation that looks so scary at the first turns out to be pretty easy to solve, because that goes to 0, that goes to 0, that goes to 0, that goes to 0. We're left with that equals that. And then even a ninth grader could then solve it to find out V equals 2GH. So you see, it's not so bad as you might at first have feared. And also one thing that's kind of interesting to know is that the velocity of the liquid that's coming out from the drain hole, the only thing that it depends on is how strong is gravity and how high is the water. Notice that rho doesn't even enter into the equation. So it doesn't matter if this liquid here, if it's water or gasoline or any liquid at all, doesn't matter. The velocity of the water that's coming out from this faucet here is going to be the same. The only thing that matters is how high is the water and what planet you're on. So because what planet you're on determines what G is. Okay. So I need to get some feedback from you guys. I'd like you to type in the chat box either yes, meaning yes, this makes sense, or no, meaning no, this doesn't make sense and you want to talk about it some more. Okay, I'm seeing lots of yeses. Yeah, okay. So one of you just sent me a private message saying, hey, this is easier than I thought it was going to be. Yeah, that's exactly it. That is the number one message that I want you guys to get from today's lesson, is that when you take next week's test and they show you Bernoulli's equation and you look at it and you say, oh no, don't be worried. Because first of all, they'll tell you the equation, so you don't need to memorize it. And then second off is they will tell you what rho is for whatever liquid it is. And from the picture, you can figure out what H is and what V is and all that. And you'll find that it's actually not that bad. Okay, so let's do another problem like the ones that I will give you in the homework tonight and like you might see on the test next week. Okay. All right, so what you see right now is a hydroelectric power plant. So let me turn on annotation here. Okay, so over on the left side, this is all the water behind the dam. So this right here is the dam. And so we got a great big reservoir, great big man-made artificial lake here. This right here is the gate where we can open and close the gate depending on how much water we want to be flowing through here. This right here is the turbine. Okay, basically it's just a fan. Think of it as a great big fan. So as the water flows through here, it rotates the fan. The fan is hooked up to a generator. Or instead of calling it a fan, I really should call it a turbine. That's the official word for it, but you can think of it as just a fan. So when the turbine turns, that makes the generator turn, that creates electricity, and out comes the electricity. Okay, so all of this generation of electricity, that's the kind of thing that an electrical engineer worries about. We're not going to worry about it today. We are going to focus on the things that a civil engineer would worry about. And so that's basically the water that's flowing through here. So what we're going to want to do is we're going to want to calculate things like how much pressure is there going to be at various points here. And we're going to calculate things like how fast is the water moving at various points. Okay, so at first glance it looks scary, but I promise you, if you're good at ninth grade algebra, it works out to be pretty easy. All right, so let's look at the type of problem that you might experience. Oops. Okay, so let's just cut off the right side of the picture just to keep things simple. Let's just look at the dam itself, at the reservoir itself. Let's suppose that the gate, so the opening or the gate that lets the water into the pipe here is 95 feet below the upper level of the water. And I want to know how much pressure is going to be pushing on the gate here. So I want to know how much pressure it is. Now, do you guys, hopefully you know what pressure is, right? Maybe we should take a minute and talk about that. So pressure is defined as the amount of force that's pushing on something divided by the area of that thing. Now, here in America, force is usually measured in pounds. And the abbreviation for pounds is not the letter P, it's actually LBS, which is kind of a weird thing. And there's a weird history behind that I don't want to take the time to go into right now. Area is usually measured in square feet. Okay, so let's say you got a hole like this. And if it's 1 foot wide and one foot tall, then it would be an area of 1 square foot. But if it's 2 feet wide by 1 foot tall, so it looks like this, okay? So then the area of that would be 2 square feet and so forth and so on. Okay, so pressure is usually given in pounds per square foot, but sometimes it's given in pounds per square inch, which is also sometimes called PSI. That means pounds per square inch. Okay, so when I asked you how much pressure is pushing on the door, first thing I'm going to need to tell you is, am I interested in using pounds per square feet or pounds per square inch? Actually, first I need to tell you, do I even want to use pounds at all? Because if you've taken physics, then you know that in civilized countries, they don't use pounds. They measure force in something called a Newton. But this is Merca. We're not nearly as civilized as some of our other friends are. And so for everything that we're going to do in the homework tonight, and I'm pretty sure in the test next week, we're going to stick with American units. So it's either going to be pounds per square foot or pounds per square inch. So you need to be familiar with working with both of those. Okay, so let's see how we would do this. Okay, so let's suppose that I want to know, first off, oops, okay, so I wasn't supposed to show you that answer. Let's suppose first that I want it in pounds per square foot, okay? So I want to know how many pounds per square foot of pressure that is, okay? So what am I going to have to do? Well, I'm going to have to use Bernoulli's equation. And so let me go back up here. Okay, so in the problem, they will always tell you what Bernoulli's equation is. All right, so here is Bernoulli's equation, which, by the way, let me just, why is it not doing this to me? Okay, hang on a second here while I come into here. So what I'm going to do is I'm going to take Bernoulli's equation. I'm going to copy that. I'm going to go down to this problem right here, and I'm just going to paste it right there, which is something I intended to do before class started and I forgot. Okay, so now that we got that, so now let's go back into here. Okay. So what do? Well, first thing you need to do is you need to decide where is point number one and where is point number two. So let's say that point number one is up here at the top, point number two is down here at the bottom. All right, so notice that the number one is open to the atmosphere. So that means the pressure there is 0. And number one, the water there is not moving, so the velocity is 0. But this guy is not going to go away. All the other things will, but that guy on that side is not going to go away. Okay, now what about on the right side? So on number two here, pressure 2, that's not going to be 0, so it's not going to go away. Notice the gate is closed. So that means that the velocity is 0, so this term is going to go away. And if we define h to equal 0 at the lowest point here, then that means this guy goes away. So this big, ugly Bernoulli's equation comes down to one very, very simple equation. The pressure then is just going to be rho times g times h. That's it. We don't even have to do any algebra other than just getting rid of these other guys. Okay, so we need to know what rho is. All right. And so in the equation or in the homework, it'll tell you what rho is. It'll tell you that for water, rho is, no, let's see, I don't want to give you the wrong number here. So hang on a second while I go down here. I forgot, oh, here it is. There is rho. Okay. Okay, so in the homework and on the test next week, they'll tell you what all these numbers are that you need to know. Okay, so then what we get is, let me turn on annotation again. Okay. Okay, so if you are using American units, rho is 1.94. Now this thing that's called a slug, I don't think I want to take the time right now to go into it. Just recognize that if you're using American units, rho is 1.94 as long as the volume is measured in square feet. If it's measured in gallons, then it's going to be different. Okay. Now, if you were using the metric system, then it would be 997. But in your homework tonight, we're not going to use the metric system. We're just going to use American system. All right, so rho then is 1.94. Okay, G, well, do we use 9.8 or do we use 32? Well, if we're using the American system, that means that 1.9, 1.94 means we're using the American system. So that means we have to use the G that Americans use, which is not 9.8, it's 32. And then H is just the height of the water, which is 95. So all we have to do then is just multiply those guys together. So 1.94 times 32 times 95. So the answer works out to be that the pressure is 5,897.6. And since we're using American units, and since we used square cubic feet down here, the units on that are going to be pounds per square foot. Okay, 5,897.6 pounds per square foot. There you go. Now, when you put in the answer into the homework tonight, it's going to tell you how many sig figs to use. And so let's stick with 2 sig figs because this number has 2 sig figs, this number has 2 sig figs. So even though this number has 3 sig figs, what determines how many sig figs you're allowed in your answer is whichever one of your input numbers has the least number of sig figs. So we need to take this number here and we need to round it off to 5,900. That will be the answer, and that's how many pounds per square foot we will get. Okay? You see, it's not so bad, right? Okay, so now, so what if I want the answer in pounds per square inch instead of pounds per square foot. Okay, so the answer that we got just now was 5,898, but that's in pounds per square feet. I want to know how many PSI it is, and PSI is pounds per square inch. Well, this is just a unit conversion problem, and you guys should be really good at unit conversions. So let's use what I like to call the Ames method for unit conversions. So I'm going to take the number that I've been given, but I'm not going to write it quite like that. I'm going to write it like this. I'm going to say 5,898. And instead of writing it like that, I'm going to write it with a horizontal line. Okay. And then I'm going to say, okay, I need to get rid of feet and convert it into inches. So how many feet equals how many inches? Hopefully you guys know the answer to that. Okay, somebody tell me, how many inches equals how many feet? Somebody tell me in the chat box. Come on. Okay, good. All right, 12. Okay, so if foot is on the bottom here and I wanted to cancel, then I have to say 1 foot equals 12 inches. Now, here's something you got to be really, really, really careful about. On the bottom here, what we have is foot squared. So that's not just foot, that's actually foot times foot. Okay. Foot squared is actually foot times foot. So if I do this, this is only 1 foot, it only cancels one of those feet. I still have another foot left over. So I need to do it a second time. Boy, I can't write very well here. Okay, so I need to do it again so that this foot can cancel out the other foot. So what I need to do then to get my answer is I have to take 5,898. I need to divide that by 12 and also divide it by another 12. Okay, and so whatever that works out to be, that will be the answer. So 5,898 divided by 12 and then divided by another 12. So the answer that I get then is 40.958. And if I'm only allowed 2 sig figs, I'll round that off to 41. And the units now are pounds per square inch. So I could write that as pound per inch squared, or I could also write it as 41 PSI. This and this both mean the same thing. Okay, what do you think? Were you good so far? What looked at first like a very difficult problem is actually not so bad, right? All right, let's do a couple more. That was too easy. Let's make it a little bit more interesting. Let's go back into here and let's say, okay, now we want to know what is the pressure that's pushing on the door. Okay, well, we've already done this problem. So let's just work through it really quickly, just to remind ourselves how we did it. Okay, so if this is point number 1, okay, this is point number 1, this is point number 2. Notice the gate is still closed. Oh, wait a minute. Oh, we've already done this. Sorry, I need to delete this page. Okay, I got them out of order. This was what I should have put first. Okay, so now here's the one that I want to do. Okay, so now we're going to open up the gate. Okay, so water is now flowing through the gate. I want to know how fast is the water going to be moving when it comes out the exit. Well, this is a problem that we've done before, right? So let's see how we do it. So first off, what equation do we need to use? Well, Bernoulli's equation is the equation we need to use, right? So where do we pick our 1 and our 2? Our 1 is going to be up here. Our 2 is going to be right here. So the left side of the equation is everything that relates to the 1. The right side of the equation is everything that relates to the 2. Okay. All right, so the surface of the water here is open to the atmosphere. So that means the pressure is 0. This reservoir is so big that even though water is coming out here, and technically, if you really wanted to argue it, you could say that these water molecules are in fact moving downward. If the reservoir is really big, this velocity here is going to be so close to 0 that we can go ahead and call it 0. All right, so what do we got? We got rho g h1. Now, if this is open to the atmosphere, then the pressure there is 0. If this is where we define our h equals 0 position to be, then this height equals 0. And h1 here is going to be 120. And so what have we got? We've got the exact same equation that we had before. So you'll notice we got a rho on each side, so that cancels out. So we multiply both sides by 2, take the square root. And so what we end up with is the equation that V equals the square root of 2 times G times H. And we know what G is, we know what H is. And so bingo, we can easily calculate what V is, right? So I'm not even going to take time to do that. We've already done it once. I don't think we need to do it again, okay? So let's suppose that we've done it and the answer that we come up with is 87.6. Now, since the units that we were using were feet, then that 87.6, the units on that are going to be feet per second. So the velocity is going to be 87.6 feet per second. Okay. Now, let's do something new. Let's say that if instead of asking you what the velocity of the water is, what if I were to ask you, what is the volume of the water that's coming out? Okay, that'll make the problem a little more interesting, right? Okay, well, we're going to need to know how big the opening is in order to answer that question. All right, so what we've got here is the problem statement tells us that the opening is a square that's 2 feet wide by 2 feet high. Okay, so if we have a square here and the area of the square is 2 feet wide by 2 feet tall, then that means the area is going to be 4 square feet. Okay, so that's the area. Well, here's a really important thing that you need to know. Write this down because this is something that they might not give you on the test. They might not tell you that, well, actually, I think they do, but just in case they don't, that the volume that is flowing, which is usually given the letter Q, which is a kind of a funny letter to use, but that's what they normally use. Q stands for what is the volume of water that's flowing, okay? That is given by the velocity of that the water is moving multiplied by the area of the opening, okay? So we already know what the velocity is. The velocity is 87.6. And so if the opening as a square hole is 2 feet wide and 2 feet tall, that means it's 4. So all we have to do then is 87.6 times 4, and that will tell us what the volume of the water is that's coming out. And so let's see what that is. So 87.6 times 4. So that means that the volumetric flow rate, which is going to be Q, is going to be 350. And then what are the units going to be? Well, if area is measured in feet and velocity is measured in feet per second, then the flow rate is going to be 350 cubic feet per second. Okay, we good? Okay, I worry that I'm going through this too fast. So give me thumbs up or thumbs down. Okay, as long as you know that Q, which is the volumetric flow rate, and you know that Q is equal to the velocity times the area, bingo, this is pretty easy. Okay, good, all right. I see that everybody's got thumbs up so far. Okay, let's take it another step further. What if I want to know how many gallons per second are coming? Okay, what if let's say we've just calculated that the volumetric flow rate is 350 cubic feet per second, but I want to know how many gallons per second that is. Well, all I need for that is I just need to know how many gallons is 1 cubic foot of water equal to. Okay, so if I take a section of water that's 1 foot wide, 1 foot tall, and 1 foot deep, okay, I need to know how many gallons does that correspond to. And it turns out that it's equal to 7.46 gallons. Okay, and that is something that you don't need to memorize, because on the test or in the homework, if you ever need to know it, that's a conversion factor that I would give to you. Okay, so so up at the top there, you may not be able to see. So 1 cubic foot of water is 7.4 gallons. So then we can just calculate what that is. Okay, so that's just a conversion problem. So let's say we've got 350 cubic feet per second. And then we're going to say that 1 cubic foot is equal to 7.46 gallons. So cubic feet cancels cubic feet. So the answer then is 350 times 7.46. So the answer then works out to be 2,613, which if we're only allowed 2 sig figs in our answer, then we should say that it's 2,600. And the units on that will be gallons per second. Okay. So tonight's homework is really not difficult at all. In fact, it's so much so that let's just take it one step further, and then I'll stop after this one next step here. I don't want you guys to be too bored by it being too easy. Okay. So actually, well, okay, here's another problem. This isn't the one that I was intending to do, but if the opening is not a square, if it's a circle, then you guys are going to need to know how to calculate the area of a circle. But I trust you can do that, right? If you've got a circle, okay, hopefully you know that the area of a circle is pi times the radius squared. And now a lot of times they don't tell you the radius. A lot of times they tell you the diameter. So then in that case, you want to say the area of the circle is the whoops, let me try that again. Okay. Then what you want to know is you want to know that the area is equal to pi times the radius, which is the diameter divided by 2 squared. Okay. So this is something that they might not give you on the test, and therefore I'm not going to give it to you in the homework. But just be aware that if it's a circle and this is the diameter, then then the method that we use will be exactly the same thing. Just calculate the velocity first, calculate how many cubic feet that is, and then calculate how many gallons that is. So that's something that you guys should be able to do okay. All right, so now let's go to the thing that I had intended to. Now let's make it a little bit more interesting here. Let's assume that we've got the turbine in place and we've got water coming, and so the water is flowing here, flows through the turbine, comes out the other side there. And let's say that we want to know what the pressure is somewhere inside the turbine there. So let's say that I want to know what is the pressure at this point right here. Okay. And so it's 120 feet below the water level, but it is not open up to the atmosphere. So what I did before was I said that the pressure up here was 0 and the pressure down here was 0 too. I cannot do that this time because it's not open to the atmosphere. In fact, this pressure right here, this is what we want to calculate. Okay. So let's see how we would do this. Well, first thing, don't be scared because the problem statement gives you everything that you need. All you need to know is where to use the stuff. Okay, so we're going to define that this position up here, this is number 1, this is number 2 down here. Number 1 is open to the atmosphere, so that's 0. Number 1 is not moving at any appreciable velocity, so it's 0. So on the left side of the equation, all we have is rho GH. On the right side of the equation, pressure is not going to be 0 this time. The velocity is not 0 either, but the problem tells you what the velocity is. Okay, and if we choose h equals 0 to be this point right here, then that thing goes away. So what we have is this equation right here. And so we know what rho is, we know what g is, we know what h is. P is what we're looking for. We know what rho is, we know what v is. So from this point on, it's no longer a physics problem. Now it's just a math problem. And you guys are good at math, right? Could a 9th grade algebra student take that equation, stick in those numbers and solve for P? I hope you could. Okay. So because we're running a little short on time here, I'm not going to do the algebra for you. I'm trusting that you guys can. And so let's assume that you do the algebra and you come up with an answer of 3,476. And because we were working in feet, the units on that are going to be pounds per square foot. Okay. Let's suppose we want to know how many PSI that is. Well, what is PSI? PSI is just pounds per square inch. So what do? The same thing we did before. We say that 3,476 pounds per square foot needs to be converted by saying that 1 foot is equal to 12 inches, but that foot only cancels one of those feet. We have to do it a second time. We have to say 1 foot equals 12 inches the second time. So that second foot cancels the last one. So then all we have to do is take 3,476 and divide it by 144, and bingo, we've got our answer. Okay. So I'm not going to actually do that for you because we've already done it once. I think that's not really time well spent. So I'm thinking we're good now. You guys should be able to do the homework now. Let me just show you really briefly what the homework is going to look like. Of course, you can go on Canvas and see it for yourself, but let's just look at it really quickly while we're all together here. So if I go into Canvas, go down here. So here is tonight's assignment, Civil Engineering 2. Everything we're doing here is called fluid mechanics. That's the name. So let me hit preview so it looks a little bit more like what you will see when you open yours up. Okay, so what you'll see here is that same water tower problem that we had before with the same numbers in it that we had before. Notice that I'm showing you Bernoulli's equation. Notice that I'm telling you what values of G are depending on whether you want feet or whether you want metric. Okay, and I'm also telling you what rho is. And so for tonight's homework problem, we're going to be working in feet. Okay, so you don't need to worry about that. You don't need to worry about that. You're going to want to use 1.94 as rho, and you're going to want to use 32 for G. And then also you're going to need to know what the density of water is, which is rho, which is, let's see, sorry, that's not the density of water. That's the density of water. Sorry, this is the conversion factor for how many gallons equals how many cubic feet. That's what this is. Okay, so all this stuff is given to you. The equation is given to you. So all you have to do then is come down here and know how to use the equations. It's the exact same equations that we just got through using. And remember that everything that we've done today is being recorded. And then later this afternoon, after school lets out, after the recording has had a little time to process, because Zoom takes a little while to process the recording. So after dinner, the recording should be posted on Canvas. If you have any problems, just go back and rewatch the recording. And I don't think you'll have too much trouble with the homework. So if you don't have any questions, you can go ahead and type "bye" into the chat box, and I will see you guys on Wednesday. If you do have a question, then tell you what, let me go ahead and turn off the recording so you can ask your question without being embarrassed.